Hello everyone, welcome back to Calculus. This time we will continue the topic in section 4.8, the L'Hopital rule. L'Hopital rule can be used to find out a limit, and the limit got to be in one of those indeterminate forms, 0 over 0 or infinity over infinity. And then the L'Hopital rule says the limit can be transformed into a new kind of limit by taking the derivative numerator and the derivative denominator. In the previous video, we worked on the case of 0 over 0. And this time, let's move on to the second case, infinity over infinity, okay? And I have two examples. They both are from the textbook. I suppose should be very simple, right? Part A, we have limit of 3x plus 5 over 2x plus 1 as x approaching to infinity. And keep in mind, infinity, it is really not a number. But anyway, you can try with some huge numbers. So as x approaching to infinity, it's fair to say numerator is getting big, right? So is denominator. So really, this is the limit in the form of indeterminate form, infinity over infinity. Then, according to the so-called L'Hopital rule, we take the derivative of the numerator, which is just 3, derivative denominator, which is 2, and it is 3 over 2. It is 3 over 2. Okay, and I hope that's easy enough. Indeed, this type of limit, we did cover this type of limit at infinity in the previous section. And really, probably we did the same example in a different way. So this time, I'm not going too far I just don't want to move back to confuse you. Okay, just let's focus on the L'Hopital rule. L'Hopital rule can be applied to another case, infinity over infinity. Okay, and the next one, I'm not sure if it's too complicated, but anyway, it is from the textbook. So I want to keep the example as it is, and also it may help to review some derivative rules. Okay, so this time I'm seeing log n of x as x approaching to 0, and you may want to know x approaching to 0. Actually, did I type it correctly? I should have typed it more accurately. It is in the fashion of x approaching to 0 from right, because x, for the logarithm, you cannot have logarithm of a negative number. It got to be positive. Besides, logarithm, log n of x as x approaching to 0, it is approaching to infinity, negative infinity. And the cotangent x, I don't want to give a lot of explanation. I still want you to know limit as x approaching to infinity, cotangent x, it is as x approaching to 0, cotangent x, it is infinity, approaching to infinity. So really, I'm saying make sure you know part of this quotient, it is in the form of indeterminate form. So then the next part, what I did, it is using the L'Hopital rule. I take the derivative of numerator, logarithm, that's 1 over x, and then derivative of cotangent x. You want to flip your textbook back to find out the derivative formula if you don't know that formula. I think it's perfectly fine. Use the textbook, do a little search, okay, on the book, find out the formula for cotangent. And for now, I'm just going to tell you the derivative of cotangent, it is negative cosecant squared. Okay. And we really don't know a lot of cotangent. We don't know a lot about the cosecant. And the one thing I want you to know for sure, cosecant, it is a reciprocal of sine. It is a reciprocal of sine. Okay. So I really could, this is what I did in the next step. I flipped this cosecant squared to the top, which turned to be sine squared. 1 over x, certainly x in the denominator. Okay. And then what I realized here is, well, remember to find our limit. We always consider direct substitution, really. That's the only way to find our limit. And this time you will see, again, it's getting into the situation. X approaching to 0, numerator is 0. Numerator is sine 0, sine squared is 0, which is just 0 squared, which is just 0. Denominator certainly is 0, right? So for this part B, the first round after using the L'Hopital rule, I get another indeterminate form 0 over 0. The limit, it is converted from infinity over infinity to 0 over 0, which means L'Hopital rule can be applied again. So from here, I apply the L'Hopital rule again, taking the derivative of the numerator. Don't forget the chain rule. Okay, sine squared of x, you consider this as a power function first, something squared. So it is 2 times sine x, then times derivative of cosine x. Derivative of denominator, which is just 1, derivative of x is 1. And again, don't forget, the way to find out the limit, it is about direct substitution. So this time I consider it as a direct substitution because denominator is 1. I really don't need to consider this 1 at all. I simply replace x with 0. I have sine 0 times cosine 0. Remember, sine 0 is 0, but cosine 0 is 1. Okay. But somewhat really doesn't matter cosine 0 because this time we are having product of sine and cosine. 0 times 1 times any number is just 0. Even this negative 2 doesn't matter. So this time the limit, it is 0. Limit is 0. So in this part, we are talking about the L'Hopital rule from section 4.8 on the textbook. L'Hopital rule will work in 2 cases. Okay, the limit in the indeterminate form of 0 over 0 certainly could be plus minus, and also in the form of infinity over infinity, and still it may involve with plus or minus. If that is the case, L'Hopital rule can be applied simply by taking the derivative of the numerator and the derivative denominator. It will change the limit into new fashion, and then hopefully to some point you can use the direct substitution. And also we mentioned, like in this part of D, example 4.38, part of D, and this should be 4.39, part of B. We realize indeed the L'Hopital rule can be applied multiple times. The thing is, okay, to find out the limit, you consider direct substitution first. If direct substitution won't work, and then now we have a new tool, the L'Hopital rule. But L'Hopital rule can only be applied when we have the limit in the indeterminate form. And I hope to this point you do realize the indeterminate forms could be of anything. Could be 0, could be 1, could be negative pi, could be 3 over 2, and it could be 0. Okay. That's all about the L'Hopital rule. And I think I have one more example. It might be a little harder, and it's not necessarily required for the exam. But anyway, I still want to give a try. I still want to present this limit to you because it's such an important limit. Okay. So the next part, I'm considering the limit as x approaching to infinity of this function. And if you take a quick look, as x approaching to infinity, it is, well, 1 over x, it is approaching to 0. So roughly, you can consider this is in the fashion of 1 to the infinity. Generally speaking, it is true. 1 to any power of number to the power of any number, it is 1. But 1 to the infinity, I just want you to know, it turns out to be the indeterminate form. Because reason is very simple, infinity is not a number. So to figure out this limit, I did something little unusual. Okay. And the way I did it here is, first of all, I take out the function as, well, I take out the expression for the limit part as a function. And then I apply the natural logarithm for this entire thing. The logarithm of y, it is the logarithm of the right-hand side, right? Remember the properties of logarithms, which really allows us to move this x down as a coefficient for the logarithm. And then I did another thing very unusual. This may look very nice, x times the logarithm. What I did, another unusual thing here is I simply moved the x to the denominator. So the x, it is changed to 1 over x, right? I hope you see this line here, really it is the same as the line in the middle. And I do have an actual reason. And the reason I want to tell you here is by doing this conversion, because really I'm thinking to consider the limit of this logarithm of y here, which is the same limit as like this. And then as x approaching to infinity, I hope you see clearly, this is 1 over x, denominator is 0. The numerator, as we mentioned earlier, okay, 1 over x, it is approaching to 0, so the numerator, it is approaching to log n of 1. But remember log n of 1, which is really 0, right? So I'm saying, when I'm considering the limit of this logarithm, it is in the form of indeterminate form, right? 0 over 0. So which means for the limit I'm considering for now, we can use the L'Hopital rule. Maybe just give a quick explanation for the denominator. I'm trying to calculate the derivative of the denominator. Certainly, if you know the derivative very well, you could just do the calculation directly, derivative 1 over x. But anyway, I'm just keeping this notation as it is, derivative denominator. And then also I calculated the derivative of the numerator. Derivative of the numerator. Logarithm of a function, it would be log n of f of x, it is f prime over f. So I have f in the denominator. Then the derivative of the numerator, or maybe put a little more work here, really it is 1 plus 1 over x, right? Derivative of the function. But anyway, derivative 1, it is just 0. So essentially, the derivative on the very top, it is the same derivative from the denominator. I'm saying those two derivatives really cancel. If you want to figure out the derivative, that's fine. They still cancel. So really, after the cancellation, I'm seeing the limit, it just turned to be x approaching to infinity, 1 over 1 plus 1 over x. And then remember, the way to find our limit, eventually we just use direct substitution. And this time, it's not about direct substitution, it is a limit at infinity. I hope it's clear. At infinity, 1 over x is 0. So the limit we are having here, it is 1 over 1 plus 0, which is, I'm sorry, this is just 1. This is just 1 here. I got this fixed. And then keep in mind that the limit I considered so far to this point, it is the logarithm of y. Y, it is a notation for this original expression. So in the end, okay, you just want to be clear, or I want to be clear, limit of this expression, it is the limit at x approaching to infinity of this y. And remember this y, if we write this y in a fancy way, it can be considered as e to the log n of y, right? Y, really, it is the same as e to the log n of y. So the limit of log n of y, as we calculated, it is just 1. So finally, I realized that such a limit of this expression, it is just e to the 1, or simply it is just e. Simply it is just e. So that should be it. that should be it. This is the limit, I believe. I think probably in the first assignment or the second assignment, there's a table asks you to fill in the values and then explain the result you got from the table. And indeed, you will see this limit. You should have seen this limit as x approaching to infinity. It is approaching to 2.718, which is just the number e. It is the Euler's number. So I think that should be it about section 4.8, L'Hopital rule. Thank you for watching. See you next time.